Hi everyone. In this video, we will go through drawing the body plot for a given system, the asymptotic body diagram indeed. And then using that body diagram, we will determine the phase margin and gain margin and crossover frequency for the system. And afterwards, we will discuss the stability of the closed loop system. So let's start by writing our A log S in the form of A log j omega. So in the frequency domain, we will have 100 times 1 plus j omega over 2 over 1 plus j omega times 1 plus j omega over 100. So one way to draw the body diagram for a system like this is to decompose it into the different components that we have here. So we have a constant value 100 times 0 at at minus 2. Then we have a pole given as 1 over 1 plus j omega, and another pole given as 1 over 1 plus j omega over 100. Then we draw the body plot for each one of the components separately, and then we add all of them to each other in order to obtain the overall body plot for the system. So let's start to prepare the graph for each case. We have the logarithmic x-axis for omega and amplitude in terms of decibel. Let's say here we have 20 decibel, 40, 60, minus 20, minus 40, and so on and so forth. And in terms of the frequency, we can say that here we have 1, 10, 100, 10 to the 3, and so on and so forth. And here we have 0 0.1, 0 0.01, and so on and so forth. So this is what we will use to draw the body plot for the amplitude, and at the same time we have the plot for the phase or angle of L of j omega. So assuming that here we have pi over 4, pi over 2, minus pi over 4, minus pi over 2, minus 3 pi over 4, minus 4, and so on and so forth. And the frequencies are the same as what we have for the amplitude plot. All right, so let's get started with the first term here, 100. For that, we have, for the amplitude, we have 20 logarithm of 100, which is equal to 20 logarithm of 10 to the power of 2, which is equal to 40 decibel. And the phase of 100 is equal to 0 all the time. So this is amplitude of 100 in terms of decibel. We can draw it. We have 40 decibel constant value here, and 0 degrees constant for the phase. Then for the next term, we have 1 plus j omega over 2, 1 plus j omega over 2. To find the corner frequency, we can write omega c over 2 equal to 1, or omega c equal to 2 radian per second is the corner frequency. Since it's a 0, and let's say that here we have omega equal to 2, since it's a 0, we will have 0 dB before that frequency, and afterwards we will have 20 decibel per decade increase. So this will be somehow the amplitude plot. And for the phase, if here we have 2 and so 2 will be somewhere, yeah, like there 2, and here 20, and here we may have 0.2. 1 decade before that we will have 0, Right at that corner frequency, we will have minus pi over 4, and 1 decade afterwards, we will have minus pi over 2. Sorry, this is a 0, so we will have plus. We'll have plus pi over 4 and plus pi over 2 1 decade afterwards. So this will be indeed the asymptotic phase plot for this component. Then let's check out the next component, which is 1 over 1 plus j omega, 1 over 1 plus j omega, for which the corner frequency is equal to 1. Therefore, until that frequency, we will have 0 in terms of amplitude, and afterwards we will have minus 20 decibel per decade as the amplitude. And in terms of phase, right at that frequency, at the corner frequency, we will have minus pi over 4. 1 decade before that, we will have 0, and 1 decade afterwards, we will have minus pi over 2. And therefore, this will be the phase plot for that component. And the last component that we have here is 1 over 1 plus j omega over 100, 1 over 1 plus j omega over 100. To find the corner frequency, we can write omega c over 100 equal to 1, or omega c equal to 100, which is, let's start by the amplitude, which is here. Since it's a pole, we will have 0 dB before that frequency, and after that frequency, we will have minus 20 decibel per decade. And in terms of phase, we will have 0 degrees until 1 decade before that. Right at that frequency, we will have minus pi over 2, minus pi over 4, and 1 decade afterwards, we will have minus pi over 2, or this will be indeed the phase plot for the last component. Now, to obtain the body plot for the whole system, we need just to add all of these with each other, put them together. Therefore, we will have until omega equal to 1, we have only constant 40 decibel. Afterwards, we see the effect of the pole. So our amplitude will start to decrease. Then at omega equal to 2, afterwards we see the effect of the 0. And until omega equal to 100, we will have a constant value, because the pole and 0 will cancel each other's effect, and we will have 0 decibel per decade. Afterwards, when we arrive at the frequency of 100, we will have minus 20 decibel per decade reduction. So here, after 1 decade, we will have this minus 20 per decibel, and 1 decade later, we will have another 20 decibel reduction, and indeed this will be our amplitude plot. So here we have omega 10 to the power of 3, 10 to 4, 10 to 5, and so on and so forth. And in terms of angle, 10 to 3, 10 to 4, 10 to 5, we need again to add everything to each other. So until 0.1, we will have 0 degrees. Then until 0.2, we will have some negative value. Afterwards, we will see the effect of the 0 appearing, and until omega equal to 10, we will have a constant value, because the phase coming from the coming from the 0 and pole will somehow cancel each other's effect, and we will have some negative value because the pole is closer to the origin than the 0. And afterwards, we will see the effect of the second pole, and the phase will start to decrease. And at omega equal to 100, we will have minus pi over 2 from the first pole, minus plus pi over 2 from the second pole, and therefore our phase will go towards this value, and we will have this phase plot. So indeed, after omega equal to 20, the 0 and the first pole will cancel each other's effect, and our phase will be quite uh, close to the phase of the second pole. So we will have something similar to this. Now we need to determine the phase margin and gain margin of the system. To determine the phase margin, we need to find out the crossover frequency for the gain, which as you can see is here. So this is omega c, the crossover frequency for the phase, which may be somewhere around, so we have 10 to the power of 3, 10 to the power of 4 here, so it may be something like 4,000 radian per second. And for that we can have a look at the same frequency which is here and check out the value of the phase for the system, which is minus pi over 2 already, and the phase margin could be determined by the distance of minus pi and this phase, which is indeed equal to 90 degrees. And in terms of gain margin, since our phase never crosses minus 180, our gain margin could be considered as infinity, because we, whatever you consider for the gain, or whatever value that you choose for the gain, you increase it till infinity, the system will not become unstable at all. So we have phase margin, gain margin, and crossover frequency. We are done with the first part. We are done with the second part. We just need to discuss the stability of the closed loop system, and that's easy now to talk about, because we have phase margin equal to 90 degrees, which is bigger than 0, and as a result the closed loop system is stable. Okay, and we are done with the question, yeah, and with the problem. So this is how you can draw the body plot for a given system, and from there you can determine the crossover frequency, the phase margin and gain margin, and discuss the stability of the system. Okay, so that's all for this video. Thanks a lot for watching, and see you next time.